Hey again, everybody. It's time for our last way to find enthalpy. This is I'm going to walk you through just a few problems. This is very easy stuff, but it's something that's very consistently used for any thermodynamic property. Today we're going to be looking at enthalpies of formation, and that's all we'll be doing, but just keep in mind that we will come back to this process again in Thermo 2, and we will do entropies of formation, and we will do Gibbs free energies of formation. But today it's just enthalpy, but we use it for a lot of stuff. So we talked about in a previous lecture about how do we find enthalpy values. We could use calorimetry. We've done that. We can use Hess's law. We've done that. Or we could use enthalpies of formation, and we're going to do that now. Real briefly, what is enthalpy of formation? So the first bullet here is kind of the definition. It's the enthalpy change that we get when we form a compound from its constituent elements. Just quickly, for example, the enthalpy of formation of water, the reaction that's associated with that would be you take hydrogen, which is in the gas state, plus O2 in the gas state, and that would form water. And we would say water would be in the liquid state, but you could also do it in the gas state, and I'll get to that in a minute. And then of course you balance the equation, so you'd have 2 hydrogens and 2 waters. So this equation represents an equation of formation. You're making water from its constituent elements. The enthalpy, just to remind you real quick, enthalpy is equal to the constant pressure heat change plus P delta V. A lot of reactions, again, the P delta V term here will not be very important, but if there's gases, like the example I just gave here, this would be one where the P delta V term would probably be important, because as these gases, hydrogen and oxygen, react to form water, you're going to have a lowering of volume, or volume reduction, so we want to keep track. But for the most part, still enthalpy is still roughly heat. The new symbol here, we looked at this before. We talk about enthalpies of formation, or the synonym for that would be heat of formation. We just give it a little F as a subscript. When we do these, the state of matter and the conditions we do them are important. So for example, most of the time we use STP conditions, which is 1 atmosphere, 25 degrees Celsius, which is standard temperature for thermodynamics. I know that's different than what you learned in gases. For gases, standard temperature was 0 Celsius. Sorry, thermo is just different. And then also standard means 1 mole. If I take these conditions for any reaction, I'm going to get a certain value of enthalpy. But if I go to 2 atmospheres, 50 degrees Celsius, and 1 mole, I'll get a different value of H. So this value of H is very condition dependent. These are called equations of state, and you'll learn about those in college. It involves calculus when you start changing things. So in high school, most everything we do is going to be standard. Because we're using standard, I want you to see this little sign right here, this little degree sign right there. Get used to that. When you see that little degree sign, that means standard enthalpy of formation. So those 1 atmosphere, 25 Celsius, don't let that confuse you. You'll see that a lot. Where do we get the values? Well, we're going to get these values out of the textbook. They already have been done years and years and years before. All of your textbooks will have an appendix in the back. So just look for a table of thermodynamic properties or something similarly labeled. Just a quick note here, elements in their standard state are assigned values of 0. Because remember, these are delta H's. So I told you in the previous lecture that it's very difficult to measure internal energies and enthalpies like in the moment. But it's much easier to find delta energies or delta enthalpies. So what we do here is we say that the formation, back to the original thing here, formation of water from its constituent elements Well, I'm saying, okay, if I start with my basic form of the elements, hydrogen and oxygen in their normal states, and go to water, I'm going to go ahead and assign the hydrogen and oxygen to 0, like that's their normal, and I'm just going to look at the change in heat associated with going to some compound state. So we're given these values of 0. That's because we have sort of standardized it to kind of make it easy, give us a jumping off point, if you will. All right, so how are we going to use these enthalpies of formation? We can use them to find the overall enthalpy change for a reaction. So remember, these enthalpies of formation were for each species in an equation, but we're going to use those to find the overall enthalpy change for a whole reaction. How do we do that? What's the justification? Well, think about this logically. When we make a reaction, we form products. So there will be an enthalpy associated with forming all of those new chemical bonds. The reactants are the opposite. Their bonds need to be broken apart. So basically you have an exothermic product formation and an endothermic reactant activity, if you will, to break those bonds. So if we just subtracted and we found the difference in energy there, because the reactants are going to be exactly opposite of what the formation is to break them apart, we can just find the difference between those two values, and that will be the leftover energy or the extra needed energy for the reaction, for the entire thing. Now I said leftover because if it's exothermic, we'll get a negative value, and that tells you it's going to be extra energy that's going to come out of the system towards you, the surroundings. And if it's endothermic, we get a positive value for this difference, and that tells you how much extra energy you need to put into the reaction to make it go. So here's the equation at the bottom. It's very simple. Products minus reactants. The N and the M are just moles because when we go to the tables and get these enthalpy values, they're going to be kilojoules per mole. So we need to multiply each reactant or each product by the number of moles from the balanced equation. All right, let's get to it. In this first example, I'm going to talk to you a little bit about what these values, what do the numbers mean, what can they tell us. But after that, you're going to get to practice on your own. So here I have a reaction, silicon tetrachloride. We're going to react it with water to make silicon dioxide and hydrogen chloride. So we're going to use this equation. And going back to the appendix in the book, I'm going to pull the values up here, but if you want to open your appendix up, the white book, it's appendix C. And, I think it's C or D also in the Zumdahl book. But for silicon tetrachloride, it's negative 640.1, water negative 285.83, and you can see the other values here. Well, what do these values really mean? Why are they negative? Remember, these are formations. So if I form, for example, let's just look at the silicon tetrachloride. If I form this from silicon plus Cl2, chlorine gas, if this value is negative, it pretty much tells me that it's easier to form the silicon-chlorine bonds in this molecule than it is to leave silicon by itself and chlorine diatomic by itself. In other words, negative values of these formations tell me that that substance is favored to be made. It's easy to make. And the more negative this value becomes, the easier it is to make that compound. If you do a quick comparison over here to silicon dioxide, this is more negative. So it's easier to make silicon dioxide than it is to make silicon tetrachloride from their respective constituent elements. All right, so now that I have these values, I want to plug in to this equation. And so I've done so, and I've kind of color-coded it so you can kind of follow. Notice that I just put the products first, and I did not forget to put my moles in. That's very important. I have 4 moles of the HCl. And then here are my reactants. This is a summation, so you add your products and you add your reactants together first, then you will subtract the products minus reactants. So keep up with your signs. That's very important in learning how to do this. Now it's just algebra. We're going to simplify these numbers. So I've done so already. I've done the multiplication first. Just keep up with those signs. This is negative here because it's plus a negative, and the same thing over here. The next step, simplify it further, do the subtractions in the brackets, and then the last step, just be simplify it down to negative 68.3. So this value, this heat of reaction, is nowhere near as much as the heats of formation for most of the species in the reaction. And that makes sense because you're breaking a lot of bonds and you're forming some new bonds. So very rarely is the heat of reaction vastly different, or of the same magnitude, I should say, of any of the formations. It's pretty close to the last one, but then again, it's still 50% off. So anyway, let's go to the next example. And here's a different reaction. This is ammonia plus oxygen. Hit pause. I want you to look at your table, look at your appendix, find the values, and work through this one. And when you're done, come back, and I'll take you through the answers, and you can check and see if you got it right. Hit pause and work it. All right, hopefully you've worked this now. So let's go through the answers. First of all, we're going to use the same formula, and let's pull up the values of each. The trick here was the oxygen. O2 is an element in its natural state, so we give that the value of 0. That's the purpose of me giving you this problem, so you see that. So when we plug in, we've color-coded it here again, products, reactants, and notice 0 for the oxygen. Then we just simplify this. I'll do it the same way. Simplify the multiplications, and then simplify the brackets. Keep up with those signs. This is a very common mistake here because we had negative, negative. And then we get negative 59.7 kilojoules per mole of reaction. Let's talk about that unit because you might be confused by that. So here's the deal. If you go back to the original equation we subbed it in, if I take any one of these and I multiply a mole times a kilojoule per mole, the mole goes away. So really, as I get to these end steps here, the units of this are just kilojoules. So technically, mathematically, it's just kilojoules. Here's where the AP wants you to fudge a little bit. The reason is here, it's negative 59.7 kilojoules for this reaction to take place. 1 mole of this reaction would include 4 moles of ammonia, 1 mole of oxygen, 2 moles of the hydrazine, and 2 moles of the water. So as long as you have 4, 1, 2, and 2 as your coefficients, that is 1 mole of the entire reaction. And the AP people in charge made a comment at a conference I went to several years ago that said they want to see thermodynamic data always in kilojoules per mole. But this isn't per mole of ammonia or per mole of hydrazine, it's per mole of the reaction as written. So I've, in a way, algebraically fudged and made up a new unit. That's just a thermo thing. Not a big deal, just remember to put moles of reaction at the end of your problems. All right, one more example. All right, had a few technical difficulties there, but even got it back on track. All right, last example is a little different. Instead of finding the heat of the reaction, I'm going to give you the heat of reaction in this problem, and we're going to look for a missing reactant or product. In this particular problem, it's a reactant. But this is very common because we can actually maybe find the heat of reaction using calorimetry, and this is a way for scientists or chemists to find the enthalpy of maybe a new compound that no one has ever done experiments on to find heats of formation. So this is actually a way to find, either verify or find for the first time, heats of formation. All right, so we're going to do that. We're going to use the same equation. And the only thing that's different about this problem is that we don't have a reactant in this case. So we're going to call it X. Now, we have to have this over here to be able to do this, but that's the only difference. The other values we can look up in the appendix. We plug them in, All right, and what I want you to do, plugging in here is not hard. Just practice the algebra. Hit pause. Go through the end now, see if you can get the algebra correct. And then come back and I'll finish it. All right, so here we go with the algebra. I've plugged in everything. I have my x here, and I did not forget to include my coefficient. It just happened to be 1 here, but be careful of that. It could be a 2x, or it could be a 3x, or a 4x, depending on what your coefficient is. So we're going to simplify this down and then solve for x. First thing I did was solve the right-hand side, simplify all the numbers to get negative 187.84 minus x. Be careful with that sign. And then I'm going to get x by itself. And this time it's negative 60.6 kilojoules per mole. And we did not find a heat of reaction this time. We found a heat of formation for calcium carbide. One last thing. It just so happened in each of these 3 examples the numbers came out to be basically the same. I think the first one was negative 68, the second was negative 59.7, and then this one was 60.6. And as I'm looking at that, I can see an error. This should not be negative. This answer should just be positive 60.6. So just a little catch by me there. So back to my point, it's just a coincidence. These numbers came out to be all relatively close at the end. So don't think if you get a number in the hundreds, it's okay. It happens. It's very common, especially in combustion reactions. These numbers can get very big. All right, so practice some more on your own with the web assigns. If you have any questions, come ask.